Hey, my friends in discrete math. This video is from section 10.3, adjacency matrices. It's pretty short, and I think it's a little bit simpler than the last section, but very, very useful and interesting. So I'm going to share my screen with you, and we'll just walk through a PowerPoint. I don't think there's really too many problems to actually do on like a whiteboard behind me, but I can talk you through the slides, and you can basically see how we can take the information in a graph and put it into a matrix so that we can store it and manipulate it. And it gives better definition and constructability and manipulative opportunity to what we're working on. So let me share my screen with you, and we'll bounce down to our PowerPoint. The inspiration today from Galatians 4. This is a book in the Bible where Paul has planted a church and all sorts of things have happened, and the gospel is sort of becoming something else. And so he writes this letter to his Galatian friends and says, what's going on? You know, this is not what I came and what I taught you, and now you're being peer pressured into things. There are these influences between grace and truth, and it's confounding you. You're not understanding what I meant. You're not living it out. And at one point, he says, have I become your enemy now by telling you the truth? There are these others, they're out to win you over, these zealous people, but not for good. They want to alienate you from us. They want to pull you away from us and toward themselves. So you're zealous for them. It's okay to be zealous, provided the purpose is good, and to be so always, not just when I'm with you. Paul's like, yeah, you're all excited when I'm with you, but always be zealous for the right reasons in the right way. My dear children, he says, I am again in the pains of childbirth until Christ is formed in you. I wish I could be with you now. I wish I could change my tone. I'm sorry I'm frustrating you. You're frustrating me, but you're perplexing me. I don't understand why we've got these problems. It doesn't seem like we ought to. But I brought that up primarily because it's so hard to speak the truth to people that are in rebellion. And it appears that in Galatia, that was the case. It wasn't just a simple misunderstanding. It was a pushback against something that they didn't want to be, because they could be more popular if they were more like the Jews that were trying to get them to believe that circumcision was a part of salvation in this context. So just remember that sometimes the most loving thing to do is a hard thing to do, and telling the truth is something that's not going to be well received, but it is the true and genuine and gracious expression of love that God asks us to extend toward each other. So there's our inspiration for the day from Galatians 4. Adjacency matrices, what we're going to try to do is to take a graph. So we've got a series of vertices and edges with connections. And that's not something that you can easily put into a computer. You could take a picture of it, but that's not well defined. So we're actually going to categorize and contain all of the information in the graph in what's called an adjacency matrix. And you can see here that essentially all you do is you count the paths, say, from A to D. And there's actually two of them, from A to D. And so over here, the rows, excuse me, the rows are the froms and the columns are the tos. And so if you want to know from A to D that there are two paths, you put a 2 in this position. This would be position 1, 4. So every position in a matrix has a unique code, almost like an XY coordinate point, but it's just a row, column location. So this one down here would be row 4, column 2. So this would be basically position 4, 2. And it's got a 1 because from D to B, there is one route. So we're just counting routes and we're storing them in their associated positions in a matrix. Pretty straightforward, and that's mostly what all of this section is. So a few examples and practice problems. Here are some adjacency matrices and their associated graphs. again, you're just, they didn't label the points over here, but you would basically label all the vertices, 1, 2, 3, 4, 1, 2, 3, 4, and then you would label them again, 1, 2, 3, 4. So we're always going to get square matrices because we're labeling the rows and the columns in the same way, so we can look at every possible combination that there is. A little more complex scenario. Too much coffee this morning. So if we have a graph that looks like this and we're counting connections, you can see there's no loops, there's no parallel edges, and for that reason, everything in our matrix down below is either a 0 or 1. If you have a number that's bigger than 1, that means you have parallel edges because there's more than one route from somewhere to somewhere else. And also, if you look at the diagonal would be like A to A or B to B or C to C. Well, the only way to go from somewhere to itself is to make a loop. So you see there's there are no loops, which is why we've got zeros on this diagonal here. This is a directed graph. And so with a directed graph, we actually don't see the same kind of symmetries that we see in an undirected graph. Basically, you can see there's a mirror image here in this undirected matrix because we're just counting paths, and to go from, say, B to F and then go from F to B, it's the same thing. It's the same count. So really, with an undirected graph, you only need half the matrix, the above the diagonal or the below the diagonal, though they pretty much fill it in all the time. But with a directed graph, we see that just because I can get to E from D, in this example, I can't get from E to D. So we go from D to E, and there's a 1 in that place. But if we look at from E to D, there's a 0 in that cell right there because we can't get from E to D, only from D to E. That's a directed graph. And also, if you look at this weighted graph, instead of the number of paths, they've actually just put into the matrix the weight, which might be a distance, it might be a cost or something like that. They put the weight into the matrix instead of the number of paths. Here's another example of a weighted graph. There actually shouldn't be an arrow right here, but basically you say to get from vertex 3 to vertex 1, it's a distance of 5. So if you look over here, from 3 to 1 is a distance of 5. You can pause the video if you want to take a look at that. All of the weights are included in the matrix. A few more examples. This one is a directed graph. And so you do not see symmetry in the adjacency matrix. So let's practice a little bit. You're going to try to create an adjacency matrix for this directed graph. And remember, you would just take all the vertices, V1, V2, and V3. You would write them down as your rows, and then you would write them down also as your columns. And this is a directed graph. So what you're going to do is you're going to count the number of ways to go from whatever's in your row heading to whatever's in your column heading. And it's the number of ways to get there, to get from, say, V1 back to V1. So there's a way to do that. So go ahead and push pause. Try to make a matrix for that. Welcome back. It should look like this. It is a directed graph, so we do not see symmetry in the matrix, symmetry about the main diagonal. We do see 2 1s on the main diagonal. That would suggest you can get from V1 to V1 one way, and there's a loop there. There's also a loop from V2 to V2. And any entry that's not a 1 would suggest parallel edges, since in this case, you can get from V2 to V3 in 2 different ways. And there's that picture associated with this matrix. Or we can go the other direction. I can give you a matrix and you can turn that into a graph, because ultimately we want to store information from a graph into a matrix, do some manipulating, do some counting, maybe modify the matrix, But then in the end, we probably want to spit out some sort of a graph so that we can see the diagram that is the result of our manipulations. However, in this case, we're just going to create an undirected graph. So you're just making connections. So go ahead and pause the video, select your vertices A, B, C, and D, and then connect them in this many ways. All right, welcome back. Whoops, I think I skipped a slide. There we go. There's the answer. So you see A and B are connected in 3 ways. B and D are connected in 1 way. C is connected to C with a loop. So again, that is the graph that results from this matrix. Turns into this graph. Or of course, remember the straightness of the connections, the locations of the points, how stretched out or compressed maybe the whole picture is, that doesn't matter. It's just the connections that occur. Here's another example of a matrix. This one is from a weighted graph. And so you can see that to go from 2 to 4, for example, has a weight of 13. So if you go from 2 to 4, that's where the 13 shows up. So we've seen that before in this slide presentation, but another good example, and you can always go back and check. Couple of properties. An adjacency matrix will be a square. N vertices means we have an n by n matrix because all the vertices are the headings of the rows, and they're also the headings of the columns. So naturally, they're going to be square. And if we have an undirected graph, we will have symmetry in the matrices. A sub ij equals A sub ji. Basically, if you move out from the main diagonal and you reverse basically sort of like an x and a y coordinate, or the subscript, if you reverse the position, the thing in position, say, 2, 3 would be the same as the thing in position 3, 2. Row, column, row, column. So those are some interesting properties. Sometimes you get disconnected graphs. And if you make a matrix of this, you can actually look in your textbook. This is an example from the textbook. But an interesting thing is if you have these, which are called connected components, in a graph that's disconnected from itself, you'll see big blocks of zeros because, for example, you can't connect 4 and 2, and you can't connect 5 and 1. And these have some counts amongst themselves, but as you cross the things in this connected component with the things in this connected component, there are no connections. So you see big blocks of zeros in the adjacency matrix, and you can check that out in your textbook. One of the things that we often do with matrices is multiply them, but it's a strange thing to multiply matrices. You actually have to take what's called the dot product, which you might remember from a physics class or maybe a pre-calculus class. So if we want to multiply this matrix by this matrix, you can't just multiply any matrix by any other matrix. Certainly you can multiply a square matrix by one of the same size. And basically you take the dot product between the row and an associated column. So if you take the dot product of row 1 by column 1, then you get the element which is going to be in position 1, comma 1. Row 1, column 1. So what you actually do for a dot product is you just take A times E plus B times G. So however many things are in this row have to also be in this column, and you multiply elements and then you add together. So that's sort of an interesting thing. Maybe in like an Algebra 2 class, you've learned how to multiply matrices like this. And you can multiply non-square matrices if they follow a particular rule, which I'll show you in just a minute. Here's another example. We've got a square matrix times a square matrix. So what do we get in this new position? Well, 1 times 1 is 1, plus 2 times 0 is 0. That turns into 1, and that's why you see a 1 up here in position 1, comma 1. This position is in 1, comma 2, row 1, column 2. So if we take row 1 dot column 2, we get 1 times 0, which is 0, plus 2 times 1, which is 2. and that's why we get the 2 there. So you can see how we've routed from this multiplication of matrices into the calculations and into the product of the 2 matrices. Here's an example where you do not have matrices of the same dimension. This is a 2 by 3. You always do rows first, by columns next. And this is a 3 by 2. And you actually can take this dot product because the number of things in the row matches the number of things in the column. So that's kind of the key to being able to multiply matrices. And you can see that matrix multiplication is not commutative. I couldn't switch these matrices around, turn them around and do this one first and this one second, because I'd have 2 things in this row. Well, let's see. I'm sorry. 2 things. Yeah, 2 things by 2 things. Maybe I could. Anyway, that's not the problem that we're doing at the moment. That's okay. So the dot product is always just element times element. So the 58, where does that come from? It comes from 1 times 7 plus 2 times 9 plus 3 times 11, and you end up getting 58. If you wanted to know what goes in this position right here, we would have to take the dot product of this row and this column. So the element in this position would be 1 times 8 plus 2 times 10 plus 3 times 12 turns into a number that goes in this position. Row 1, column 2. We'll practice that in a minute. In order to be able to multiply matrices, if your first matrix is of dimension n by n, so row by column, and your second one is of dimension n by p, row by column, the inner dimensions must match. In other words, the columns of the first must match the rows of the second, and the resulting matrix will be an m by p matrix. This is a really important slide because it tells you if you can multiply your matrices and what size your resulting matrix will be. So we've got a 2 by 4, and then we've got a 4 by 3. Since the columns in the first matrix match the rows of the second matrix, you can see we got the same size here and here, which means we're allowed to do this multiplication. And the result, since this is a 2 by 4 and this is a 4 by 3, the resulting matrix would be a 2 by 3. A 2 by 3. The rows of the first by the columns of the second. And so your first element in the 1, 1 position would be 1 times 1 plus 4 times 2 plus 6 times 9 plus 10 times 3. That's a number. That's the dot product of this row and this column. And that would be the element you get in position 1, 1 of your new matrix. Then, of course, you're going to have to do all of this dot all of that. You're going to have to do all of this dot all of that. And then you'll have to do it 3 times with this dot this dot in the middle, and then this dot the end. So quite a bit of work. You actually can type this into a graphing calculator, matrix A and then matrix B under the matrix headings, and then you can just type matrix A times matrix B, and it will do it. You can store that into, say, matrix C, and your calculator will multiply matrices for you. It's tedious and long if you're doing it by hand, but it's actually fast and easy with the calculator. By the way, if you were to multiply those out, your resulting matrix would be a 2 by 3, and it would be this. So if you want to go back and practice that, you can check your work. A couple of other things with regard to matrices. If you've taken linear algebra or differential equations or some great class like that, you'll recognize this. This is the identity matrix. It's a square matrix with 1s on the diagonal, 0s above and below. And if you multiply any square matrix by this, a 3 by 3 by this, then the return to you is the same matrix. It's like 1 in matrix multiplication. If you times by 1, you get the number back. If you times a square matrix by this, you get that square matrix back. We can have identity matrices of different sizes. Here's a 2 by 2 identity. Here's a 3 by 3, a 4 by 4. That should say I4. So that's kind of useful. And we can have an identity matrix that's square of any size we want. But again, the ones are on the diagonal, and you have zeros above and zeros below. All right, so that's it. Pretty straightforward, I think. I think you'll find these homework problems are maybe a little easier and less creative than some of the other ones, but maybe not quite as interesting. So let me just leave it at that. And the next section, the next video will be on isomorphisms of graphs. Graphs that don't look the same, but really functionally are the same. They do the same things, and how to identify that. So we'll look forward to that. But until then, I will look forward to seeing you.